The expansion of the universe is a foundational concept in cosmology, revealing much about the universe's past, present, and future. It describes how space itself stretches, causing galaxies to move away from one another over time. Unlike a conventional explosion where objects travel outward into empty space, the expansion of the universe means that space itself is growing, carrying galaxies along with it. This idea was first discovered by astronomer Edwin Hubble in 1929, who observed a fascinating pattern in the behavior of distant galaxies. Hubble noticed that the light coming from galaxies was redshifted, meaning the wavelengths were stretched toward the red end of the spectrum. This indicated that the galaxies were moving away from Earth. More importantly, the farther a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, provided direct evidence that the universe was expanding. The logical conclusion was that the universe must have been much smaller and denser in the distant past, leading to the concept of the Big Bang, a moment around 13.8 billion years ago when the universe began expanding from an extremely hot and dense state. This discovery reshaped our understanding of the cosmos, showing that the universe is dynamic, not static as previously thought. The redshift of galaxies was not the only evidence of expansion. In the 1960s, scientists discovered the cosmic microwave background radiation (CMB), a faint glow of radiation left over from the Big Bang. This relic radiation permeates the universe and provides a snapshot of its infancy, offering further confirmation of its expanding nature. The universe's expansion is driven by the stretching of space itself. To visualize this, imagine a balloon with dots on its surface. As the balloon inflates, the dots move farther apart, not because they are moving on their own but because the balloon's surface is expanding. Similarly, galaxies are carried apart as the fabric of space grows. This phenomenon occurs on vast cosmic scales, and while galaxies move away from each other, the gravitational forces within individual galaxies keep them bound together. One of the most surprising discoveries in modern cosmology came in the late 1990s when scientists found that the expansion of the universe is accelerating. This was unexpected because gravity, which pulls matter together, should theoretically slow the expansion over time. To explain this acceleration, researchers proposed the existence of dark energy, a mysterious and unseen force that constitutes about 68% of the universe. Dark energy is thought to act as a repulsive force, counteracting gravity and driving galaxies apart at an increasing rate. The implications of an accelerating universe are profound. If this trend continues indefinitely, the universe could face a big freeze, where galaxies become so distant from each other that stars eventually burn out, leaving a cold, dark, and lifeless cosmos. Alternatively, if dark energy's effects intensify, it could lead to a big rip, tearing apart galaxies, stars, and even atoms. These scenarios highlight the delicate balance between dark energy and gravity in shaping the universe's future. While the expansion of the universe dominates on large scales, it does not affect smaller structures like galaxies, solar systems, or atoms. These remain intact because their internal forces, such as gravity and electromagnetism, are much stronger than the effects of expansion. However, on a cosmic scale, the influence of expansion is undeniable and has shaped the distribution of galaxies, stars, and other celestial objects over billions of years. The concept of an expanding universe also challenges our perception of space and time. It implies that the universe had a beginning, a moment when space, time, and matter came into existence. This raises profound questions about what, if anything, existed before the Big Bang, as well as the ultimate fate of the cosmos. Scientists continue to explore these mysteries, using advanced telescopes and simulations to refine our understanding. In recent years, observations from instruments like the Hubble Space Telescope and the James Webb Space Telescope have provided unprecedented insights into the universe's expansion. These tools allow us to observe galaxies at different stages of their evolution, helping scientists map how the universe has changed over billions of years. Such research deepens our knowledge of dark energy, dark matter, and the intricate interplay of forces that govern the cosmos. The discovery of the expanding universe also emphasizes humanity's place in the vastness of the cosmos. It reveals that Earth, our solar system, and even our galaxy are just small parts of an ever-growing and evolving universe. This perspective inspires both awe and curiosity, driving us to ask questions about the origins of life, the nature of reality, and the possibilities of existence beyond our planet. The expansion of the universe also introduces the concept of a cosmic horizon. As galaxies move farther away, they can reach speeds faster than the speed of light relative to us due to the stretching of space. This means that light from those galaxies will never reach us, effectively placing them beyond our observable universe. This limit reminds us of the vastness of the cosmos and the fact that much of it remains inaccessible to observation. Scientists are now studying the early universe in more detail to understand the forces that set the expansion in motion. By analyzing the distribution of galaxies and the properties of the CMB, researchers hope to uncover clues about the nature of dark energy and its role in the universe's evolution. These investigations are critical for addressing fundamental questions about the laws of physics and the structure of spacetime. The idea that the universe is expanding challenges the notion of a static, unchanging cosmos, which was a widely held belief for centuries. Instead, it paints a picture of a dynamic, ever-evolving universe where change is a fundamental aspect of existence. This understanding has profound implications for science, philosophy, and our broader worldview. Ultimately, the expansion of the universe is more than a scientific discovery, it is a story of growth and transformation. It tells us that the universe is not a fixed entity but a living, breathing system that changes over time. This realization invites us to explore not only the physical laws that govern the cosmos but also the deeper questions about its purpose and meaning. The journey to understand the universe's expansion is far from over. Each new discovery brings us closer to unraveling the mysteries of dark energy, the Big Bang, and the ultimate fate of the cosmos. As we continue to push the boundaries of knowledge, we are reminded of the limitless possibilities that lie ahead in our quest to understand the universe. The evidence for the expansion of the universe comes from multiple observations, each offering profound insights into the cosmos's behavior and history. One of the earliest pieces of evidence is the redshift of light from distant galaxies. When light from these galaxies reaches us, it is stretched to longer wavelengths, shifting toward the red end of the spectrum. This phenomenon, called redshift, occurs because the space between galaxies is expanding, stretching the light waves during their journey. Edwin Hubble's observations in 1929 demonstrated a direct relationship between a galaxy's distance and its redshift, leading to the conclusion that the universe is expanding. The redshift of galaxies reveals that they are moving away from us, and the farther they are, the faster they recede. This relationship, encapsulated in Hubble's law, provides a cornerstone for modern cosmology. It implies that the universe was once much smaller and has been expanding over time. Importantly, this redshift is not due to galaxies moving through space like objects in motion but because space itself is stretching, carrying galaxies along with it. This distinction is crucial to understanding the nature of cosmic expansion. In addition to redshift, another key piece of evidence comes from the cosmic microwave background radiation, CMB. Discovered in the 1960s, the CMB is a faint glow of radiation that permeates the universe. It is the afterglow of the Big Bang, representing the heat left over from the universe's infancy. At the time of the Big Bang, the universe was extremely hot and dense, and as it expanded, this heat spread out and cooled. Today, the CMB is detectable as microwave radiation with a nearly uniform temperature of about 2.7 Kelvin. The CMB is a snapshot of the universe when it was about 380,000 years old, a time when it first became transparent to light. Before this point, the universe was an opaque plasma of particles, but as it expanded and cooled, atoms formed, allowing light to travel freely. The patterns in the CMB provide a wealth of information about the universe's early conditions, including its density, composition, and rate of expansion. These patterns are consistent with predictions of an expanding universe and support the Big Bang model. Another significant line of evidence comes from the large-scale structure of the universe. When we observe the distribution of galaxies across cosmic scales, we see patterns of clusters, filaments, and voids. These structures align with theoretical models that describe how matter should have clumped together over time under the influence of gravity in an expanding universe. Without expansion, these large-scale patterns would not match the observed distribution of galaxies. The large-scale structure also reveals the role of dark matter, an unseen form of matter that makes up about 27% of the universe. Dark matter interacts gravitationally, helping galaxies and clusters form, but does not emit or absorb light. Its presence and behavior further support the idea of an expanding universe, as it helps explain how structures evolved from the nearly uniform state observed in the CMB to the complex arrangement of galaxies we see today. Redshift measurements have been refined over decades, with modern telescopes observing galaxies billions of light-years away. These observations allow scientists to look back in time and study how the rate of expansion has changed. By comparing redshifts at different distances, researchers have confirmed that the universe's expansion is not only ongoing but also accelerating. This acceleration, discovered in the 1990s, added a new layer to our understanding and pointed to the existence of dark energy. Dark energy, a mysterious force driving the acceleration, constitutes about 68% of the universe. Its effects are evident in the increasing distances between galaxies over time. While its exact nature remains unknown, dark energy's role in cosmic expansion is undeniable. Combined with the evidence of redshift, the CMB, and large-scale structure, it reinforces the conclusion that the universe is expanding at an accelerating pace. The redshift, CMB, and large-scale structure collectively form a robust framework of evidence for cosmic expansion. Each piece complements the others, creating a consistent picture of a universe that began in a hot, dense state and has been growing ever since. These observations also align with predictions from Einstein's general theory of relativity, which describes how space and time are shaped by matter and energy. The discovery of redshift was a groundbreaking moment, challenging the notion of a static universe. It revealed that the cosmos is dynamic and constantly changing. Similarly, the CMB confirmed the theoretical predictions of the Big Bang, offering a glimpse into the universe's earliest moments. Together, these findings transformed cosmology into a precise science, allowing researchers to test hypotheses and refine models with incredible accuracy. Large-scale galaxy surveys have provided further confirmation of expansion by mapping the positions and velocities of millions of galaxies. These surveys show that galaxies are not randomly distributed but form intricate patterns shaped by the interplay of gravity and expansion. The observed structures match predictions from simulations based on an expanding universe, adding another layer of validation. The combination of these lines of evidence has allowed scientists to estimate the universe's age and size. By measuring the rate of expansion, known as the Hubble constant, and studying the CMB, researchers have calculated that the universe is approximately 13.8 billion years old. Its observable size, however, continues to grow as the expansion carries galaxies farther away. These discoveries have profound implications for our understanding of the universe's origins and fate. The evidence for expansion shows that the cosmos is not eternal but had a beginning. This realization raises questions about what preceded the Big Bang and what lies beyond the observable universe. While such questions remain speculative, they inspire ongoing exploration and inquiry. In essence, the redshift of galaxies, the CMB, and the large-scale structure collectively weave a compelling narrative of an expanding universe. These phenomena, observed across vast distances and timescales, provide a consistent and robust framework for understanding the cosmos. Each piece of evidence adds depth to our knowledge, revealing a universe that is both dynamic and awe-inspiring. The expansion of the universe is a unique and mind-bending phenomenon that challenges our everyday understanding of motion and space. Unlike objects moving through a pre-existing medium, the expansion of the universe involves the stretching of space itself. This means galaxies are not flying away from each other through space. Instead, the space between them is increasing. This subtle but profound distinction underlies the nature of cosmic expansion and sets it apart from ordinary motion. To visualize this concept, imagine a rubber sheet with dots drawn on its surface. As the sheet stretches, the dots move farther apart not because they are moving on their own, but because the sheet is expanding. Similarly, galaxies remain relatively stationary within their local regions of space, while the fabric of space stretches, increasing the distances between them. This effect is more pronounced at larger scales, where the cumulative stretching becomes significant. One important aspect of expansion is that it does not affect systems bound by gravity. For instance, galaxies, solar systems, and atoms remain intact despite the expansion of space. This is because the forces holding these systems together, such as gravity and electromagnetism, are much stronger than the effect of expansion on small scales. As a result, while galaxies drift apart from each other over billions of years, the structures within them remain stable. The discovery that the universe's expansion is accelerating was a groundbreaking moment in cosmology. In the late 1990s, observations of distant supernovae revealed that galaxies were receding at increasing speeds. This unexpected finding introduced the concept of dark energy, a mysterious force responsible for driving the acceleration. Dark energy acts as a kind of anti-gravity, pushing galaxies apart faster as time goes on. Dark energy is now estimated to make up about 68% of the universe, making it the dominant component of the cosmos. Despite its significant influence, its exact nature remains unknown. Scientists hypothesize that it could be related to the energy of empty space itself, sometimes referred to as the cosmological constant, or it might arise from an entirely new field of physics. Understanding dark energy is one of the most significant challenges in modern cosmology. The role of dark energy becomes more evident when considering its effect on the rate of expansion. Initially, after the Big Bang, the universe's expansion was decelerating due to the pull of gravity. However, as the universe grew larger and matter became more spread out, the influence of dark energy began to dominate, reversing the trend and causing acceleration. This transition has profound implications for the universe's future. The accelerated expansion driven by dark energy suggests that the universe is heading toward a state where galaxies will become increasingly isolated. Over billions of years, galaxies that are not gravitationally bound to one another will drift so far apart that their light will no longer reach us. This scenario, known as the Big Freeze, predicts a cold, dark, and lifeless cosmos in the distant future. The mechanism of expansion also explains why we observe the cosmic redshift. As space stretches, the wavelengths of light traveling through it are also stretched, shifting them toward the red end of the spectrum. This redshift is a direct indicator of the universe's expansion and provides a way to measure how fast it is occurring at different points in time. Observing this redshift has been crucial in confirming the accelerating expansion. Despite its mysterious nature, dark energy is well supported by observations, including those of the Cosmic Microwave Background (CMB), large-scale galaxy surveys, and supernovae data. These independent lines of evidence all point to a universe dominated by a repulsive force that counteracts gravity on the largest scales. This force plays a key role in shaping the universe's evolution and determining its ultimate fate. Dark energy also raises deep questions about the nature of space and time. If it is indeed a property of space itself, then its effects would grow stronger as the universe expands because the amount of space increases. This could lead to scenarios where dark energy eventually overwhelms all other forces, causing a catastrophic event known as the Big Rip, where even atoms are torn apart. The discovery of dark energy has transformed our understanding of cosmology, forcing scientists to rethink fundamental assumptions about the universe. It has also highlighted the limitations of current theories, such as general relativity, which cannot fully explain the properties of dark energy. This has prompted the search for new physics that can bridge the gap in our knowledge. One of the most striking aspects of the universe's expansion is its uniformity. Observations show that expansion occurs at the same rate in all directions, a property known as isotropy. This uniformity reflects the underlying simplicity of the cosmos on large scales, even as it exhibits complex structures like galaxies and clusters on smaller scales. Dark energy plays a role in maintaining this isotropic expansion. The interplay between dark energy and gravity determines the universe's large-scale structure and its future. While gravity pulls matter together to form galaxies and clusters, dark energy drives them apart. This cosmic tug-of-war defines the balance of forces that shape the evolution of the universe. Over time, as dark energy becomes increasingly dominant, the influence of gravity on large scales diminishes. The expansion of the universe is not just a physical phenomenon, it has profound philosophical implications. It challenges our perception of space, suggesting that it is not a static backdrop but a dynamic and evolving entity. It also forces us to consider questions about the nature of existence, the origins of the universe, and what lies beyond the observable cosmos. The accelerating expansion also limits what we can observe. As galaxies move beyond the cosmic horizon, their light will no longer reach us, effectively making them invisible. This shrinking observable universe underscores the vastness of the cosmos and the finite nature of our knowledge. It also emphasizes the importance of studying the universe now, while much of it remains within reach. Understanding how expansion works and the role of dark energy is central to unraveling the mysteries of the universe. These phenomena are not just abstract concepts but key to answering fundamental questions about where we come from and where we are headed. They remind us of the dynamic and ever-changing nature of the cosmos and our place within it. Ultimately, the expansion of the universe and the presence of dark energy tell a story of growth, transformation, and the profound interconnectedness of all things. As we continue to study these forces, we gain not only scientific insights but also a deeper appreciation for the vast and intricate cosmos that surrounds us. The expansion of the universe has profound implications for its future, with several possible scenarios depending on the nature of dark energy and its interplay with gravity. The first possibility, known as the Big Freeze, envisions a universe where expansion continues indefinitely. In this scenario, galaxies will drift farther apart over billions of years, eventually becoming isolated from one another. As the distances grow, the energy supply that fuels stars will dwindle, leading to a gradual cooling and dimming of the cosmos. Over unimaginable timescales, stars will burn out, black holes will evaporate, and the universe will become a cold, dark, and lifeless expanse. The Big Freeze is often considered the most likely outcome based on current observations. As the expansion accelerates due to dark energy, it drives galaxies away from one another faster than the speed of light. This doesn't violate physics because it is space itself that is expanding, not the galaxies moving through it. Eventually, the observable universe will shrink as light from distant galaxies will no longer reach us. The cosmic horizon will contract, leaving us in an increasingly isolated and empty universe. Another potential future is the Big Rip, which occurs if the influence of dark energy intensifies over time. In this scenario, the force driving the universe's expansion would not remain constant but would grow stronger, overpowering all other forces. Galaxies, stars, and even planets would be torn apart as the fabric of space itself becomes unstable. In the final moments of the Big Rip, even the atoms and subatomic particles that make up matter would be shredded, resulting in the ultimate disintegration of the universe. The Big Rip depends on the nature of dark energy, which remains poorly understood. If dark energy is not a constant but instead varies over time, its effects could intensify to catastrophic levels. While current evidence suggests that dark energy behaves like the cosmological constant proposed by Einstein, slight variations in its behavior could lead to this extreme and dramatic end to the universe. A third possibility, the Big Crunch, represents a reversal of the universe's expansion. This outcome would occur if gravity eventually overcomes the influence of dark energy, halting the expansion and causing the universe to collapse back on itself. Galaxies would move closer together, temperatures would rise, and matter would become increasingly dense. In the final stages, the universe could return to a hot, dense state similar to the conditions of the Big Bang. This process might even trigger a new cycle of expansion and contraction, leading to a cyclic universe. The Big Crunch is less likely based on current observations, as the evidence strongly supports an accelerating expansion rather than a slowing or reversing one. However, the possibility cannot be completely ruled out, especially if our understanding of dark energy evolves or if its effects diminish over time. A universe that ends in a Big Crunch might give rise to new universes, posing fascinating questions about the cyclical nature of existence. The fourth scenario is one of steady expansion, where the universe continues to grow at a balanced rate. This outcome would allow structures like galaxies, stars, and planetary systems to persist for much longer. Dark energy would still drive expansion, but without accelerating to the point of causing a big rip. This equilibrium could maintain a dynamic but habitable universe, albeit one where the distances between galaxies become vast over time. Steady expansion is an intriguing possibility because it implies a long-lasting universe where life and complexity might continue to evolve. In this scenario, while the observable universe would still shrink as galaxies recede beyond the cosmic horizon, the fundamental structures within gravitationally bound systems like galaxies would remain intact, preserving local environments where stars and planets could form. The ultimate fate of the universe depends critically on the precise nature of dark energy, which remains one of the greatest mysteries in cosmology. If dark energy remains constant, as current models suggest, the Big Freeze is the most likely outcome. However, if it varies in strength or interacts with other cosmic forces in unexpected ways, alternative futures like the Big Rip or Big Crunch become possible. Understanding dark energy is essential to predicting which of these scenarios will unfold. The expansion also raises philosophical questions about the meaning of an infinite, empty, or cyclic universe. If the Big Freeze occurs, the cosmos will eventually reach a state of maximum entropy, where no energy is available to do work. This so-called heat death of the universe represents the ultimate decline into disorder, challenging our understanding of time and existence. On the other hand, a cyclic universe that undergoes repeated expansions and contractions could suggest a more dynamic and perpetual cosmos. Despite these uncertainties, the study of the universe's expansion has provided invaluable insights into its past and present. Observations of the cosmic microwave background radiation, the redshift of galaxies, and large-scale structures have revealed the mechanisms driving the universe's growth. These discoveries allow scientists to create models that predict its future, even as they grapple with the unknowns surrounding dark energy and the ultimate fate of space and time. Each scenario offers a unique perspective on the universe's destiny, emphasizing the interplay of forces that shape its evolution. The Big Freeze and Big Rip highlight the dominance of dark energy, while the Big Crunch underscores the enduring power of gravity. Steady expansion represents a delicate balance between these forces, offering a more stable but still evolving cosmos. The future of the universe is a compelling mystery that invites both scientific investigation and philosophical reflection. Whether the cosmos ends in a cold, dark expanse, a violent disintegration, a fiery collapse, or a stable equilibrium, its story is one of transformation and wonder. The study of cosmic expansion not only reveals the mechanics of the universe but also inspires a deeper appreciation for its vastness and complexity. The concept of an expanding universe fundamentally alters our understanding of time, space, and existence. It reveals that the cosmos is not a static entity but a dynamic and evolving system with a definitive beginning. This realization, rooted in the Big Bang Theory, suggests that the universe has transformed over billions of years and will continue to do so, offering a profound narrative of creation and change. The notion that space itself stretches challenges our conventional ideas of motion and distance, reshaping how we perceive the cosmos and our place within it. The expanding universe provides a framework for exploring fundamental mysteries, such as the nature of dark energy and dark matter. These enigmatic forces, which make up most of the universe's mass energy content, hold the key to understanding why the expansion is accelerating and how the cosmos will evolve. Tools like the James Webb Space Telescope enable scientists to peer into the distant past, studying the early universe and uncovering the forces that drive its evolution. These observations not only deepen our knowledge of cosmic history but also refine our predictions about the future. This expansion also has profound philosophical implications. It tells a story of interconnectedness and transformation, reminding us that all matter, including ourselves, originated from the same initial state. The universe's dynamic nature underscores the fleeting and ever-changing character of existence, prompting reflections on the impermanence of the cosmos and our role within it. It raises questions about the meaning of time and the possibility of infinite cycles or new universes arising from the current one. As we study the expanding universe, we also grapple with the limits of our knowledge. Concepts like dark energy and the nature of space-time remain elusive, pushing the boundaries of physics and challenging our understanding of reality. The search for answers inspires innovation in science and technology, driving the development of advanced instruments and theories. Each discovery brings us closer to unraveling the intricate tapestry of the cosmos while reminding us of the vastness yet to be explored. In essence, the expanding universe is more than a scientific phenomenon. It is a profound narrative of creation, transformation, and infinite possibilities. It encourages humanity to embrace curiosity and wonder, inspiring a deeper connection to the cosmos. Through this exploration, we gain not only knowledge of the universe's mechanics but also a richer appreciation of its beauty, complexity, and the unique privilege of observing its unfolding story.